Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome to another episode of the Reliability Matters podcast. I'm Mike Conrad. For those of you who are keeping track, this is episode number 111. Historically, circuit assemblies are rigid devices. IoT, or Internet of Things, has opened up the opportunity to embed electronics into a near limitless array of form factors. Some of these form factors require the electronic assembly to be flexible, such as in wearable or perhaps medical applications. To complicate matters, the metal conductors on the assembly historically have been rigid, as I mentioned before, and not flexible or malleable. That may change with the adoption of liquid metals. We were all exposed to the concept of liquid metal, probably back in high school in science class when we played with Mercury, or perhaps in the 1991 film Terminator 2 with the liquid metal villain, the T-1000. Will science fiction become reality? My guest today is Dr. Michael Dickey. Michael is currently the Camille and Henry Dreyfus Professor in the Department of Chemical and Biomolecular Engineering at North Carolina State University. Michael received a Bachelor's of Science in Chemical Engineering from Georgia Institute of Technology and a PhD from the University of Texas. From 2006 to 2008, he was a post-doctoral fellow in the lab of Professor George Whitesides at Harvard University. Michael completed a sabbatical at Microsoft in 2016. Michael's research interests include soft matter, liquid metals, gels, and polymers, for soft and stretchable devices, electronics, energy harvesters, textiles, and soft robotics. And hopefully, for the sake of humanity, not liquid metal T-1000 villains. So without any further ado, I welcome Dr. Michael Dickey to the show. Michael, thanks for joining me today. I'm so thrilled you're my guest.
Thank you, Mike. I'm excited to be here and honored. Thank you.
Well, thank you. So your work is fascinating. I've watched a few of your past interviews, and I can't wait to share it with my audience. How does one wake up one morning with an interest in liquid metal? I find liquid metal fascinating, clearly. But before I let you answer that, when I was first exposed to the concept of liquid metal, of course, back in high school, in science class, as most kids probably were, only back in my day, the science teacher had us all stand up kind of shoulder to shoulder, put our palms out, and poured a little drop of mercury in each of our hands. And we were able to play with it. Of course, some kids dropped it, and then it just scattered into a million little tiny balls. And we were, picking it up with sheets of paper, trying to get it all to, join back together again. Probably not the safest experience in the world from what we know about mercury today. I don't know if we didn't know about mercury today, but I think that was just a different time. I would imagine the teachers probably smoking a cigarette with one hand and putting mercury out in students' hands with the other. How did your interest in liquid metal come about?
Well, it's funny that you mentioned that. Whenever I give talks on this topic, I usually ask people, what is the first thing you think of when you hear the term liquid metal? And they either say Mercury for the reasons that you just mentioned, or they'll say Terminator. And unfortunately, those are two things with sort of negative connotations. And I've been slowly trying to change that perception.
Although Mercury might kill you slowly, the Terminator probably doesn't take that much time.
Yeah, that's right.
Yeah.
So my foray into this material began when I was a postdoc. So my PhD actually was on polymers, and specifically polymers for making computer chips, photolithography, photoresist, those kinds of things, which I'm sure most of your listeners know about. And so it was also a little bit of a strange topic for me. And if you'd asked me, 15, 20 years ago, liquid metal, I would have said also Mercury or the Terminator. But it was during my postdoc that I got kind of started learning about this, started getting exposed to this topic. And the way that I got involved was that one of my lab mates was using liquid metals, not mercury, but gallium and gallium-based alloys, which is what we're going to talk about today. And he was using them to make very simple electrodes to surfaces. So if you imagine you have a surface, could be a silicon wafer or something like that, and you want to make an electrical contact to it, one way to do it is to just put a droplet of liquid metal on the surface. And he noticed that when he tried to pull the droplet off the surface, it was sticking to the surface. And not only was it sticking, but it was forming a cone shape, kind of like what would happen if you stretch, had bubble gum and you pull on bubble gum, it would thin in the middle and form a cone-like shape. And so that was very weird because liquids typically don't do that. If you tried to do that with water, you'd end up with a hemispherical structure. And so that got me interested. And one of the punchlines from this that we're going to talk about is the reason it does this is it's a liquid, but on its surface it reacts with air and forms a very thin oxide. And oxide is like just another fancy word for glass.
So it's not a surface tension difference. It's an oxide that's causing it to semi-coagulate on a thin layer on the top. Is that correct?
Exactly. So it reacts very, very quickly with air and forms an oxide. And that oxide is about 3 nanometers thick. So if those words don't mean a lot to you, your diameter of your hair is about 100 microns. And so this is like, I don't know, I have to do the math in my head real quick, but it'd be like 30,000 times thinner, something like that.
That's funny because to me, it's more intuitive that something that thin would not have that much shaping power, right?
Yeah.
It's not much, yet it's still able to affect the shape and keep it from flattening out or keep it from rounding out or whatever natural form it wants to take.
Yeah, exactly. So I usually tell people it's kind of similar to a waterbed where you've got water or liquid on the inside and then you've got the shell. But to your point, because the shell in this case is so thin, it's really only strong enough to hold structures that are small. So like say less than a millimeter or so. Mm-hmm. But, in the world of electronics, that's a relevant length scale. If you're going to make a wire or something like that, it's strong enough to hold that shape. Now, the reality is if you touched it with your hand, it's very easy to break. So usually what we do is, we use this shell to basically pattern the metal into shapes that would normally not be allowed by surface tension. Sure. So most liquids are going to form droplets. Here we want to form it into wires or antennas or different shapes like that. And then ultimately we embed it into rubber so that it's kind of like wet paint. So if you leave it exposed, it would be very easily smear. But by encapsulating it, just like you would do with any other electronics, you typically have some packaging that you put the electronics in. And here the packaging just happens to be stretchy.
Yeah. And we've used liquid metal, and I'm thinking of Mercury now, in electrical/electronic, mostly electrical applications, probably more applications than I'm aware of, but the ones I am aware of are things like switches, thermostats, typically have a bulb with mercury in it, and connected to a spring that changes orientation based on temperature, and it sloshes the mercury to one end of the switch to open or close it. I remember when I was a kid, mercury light switches came out, and all of a sudden there was no more click. There was no more spring-loaded switch. It was a mercury switch, which made them very silent when you turn them on and off. And I'm sure there are probably other applications, maybe heat dissipation applications or something that liquid metals of some sort have been in electronics. And what do you view as an application, before we get into the science of liquid metal and its shape-shifting capabilities that that you talk about? What are some of the applications that gallium, in this case, would find in electronics, and what would that outcome be for electronics? What can we do with that we currently can't do or can't do well based on non-liquid technology, the kind of historical technology?
Right. So the thing that got me personally interested in this topic and got me engaged is the idea of making electronic devices that are soft and stretchable. So, your cell phone or your laptop or pretty much any conventional electronics are rigid. And the notion with the liquid metal is that it's literally as soft as water. So if you could pattern it into wires, interconnects, antennas, these types of structures, then you could start to imagine devices that could be truly stretchable. So it's just one example, and we'll maybe talk about this in just a little bit. But as one example, if you put it as kind of the simplest example, actually, I'll say, is if you can just imagine putting the liquid metal in a rubber tube, you have now formed a wire that is as stretchable as the rubber tube. So it's, imagine something like a rubber band, but it's as conductive as a metal. So you kind of get the best of both worlds. And that was what it initially got me excited. I think later we'll probably talk about other applications, but in terms of the electronics space, like that's really a distinguishing thing. There's, as best I know, there's nothing that can come close to the combination of stretchability and conductivity that's enabled by these gallium alloys.
Clearly a wire is malleable, right? So that's good. You can shorten it, but this is your limit here. You cannot make it any longer. So if you have a device that, or an application that requires a stretchy conductor, you either currently have to put a large service loop in there to allow a little extra lengthening, but you're still limited. When you get to the end of that service loop, it's a hard stop, right? You pull it any harder, it'll break. So yeah, that's an interesting application for something that I can imagine some kind of wearable where it's, you put it on flat, but then you have the need to curve it. All of a sudden, when you curve it, you need to stretch out the conductors, and historically they don't stretch; they break. So
yes.
Yeah, that's an interesting application.
Yeah, I mean, so you hit on this really nicely. So actually, this is going to date my phone here, but I've got an example of exactly what you said, an old phone cord cable, which is basically taking advantage of geometry. So even the wire that you showed, which is just a straight wire, the reason that you can flex it is because it's sufficiently thin. And, a good example of this from our day-to-day lives is wood. We use wood to build our houses typically, but if you make it thin enough, you have essentially a piece of paper. And paper is flexible, but a 2x4 is not very flexible. So it's really just taking advantage of, kind of what other people have done is taking advantage of geometric tricks, making things thin or using serpentine type shaped lines that can stretch just because of geometry, but not because of their inherent mechanical properties.
Right.
And so that's what the liquid metal allows us to do. And, you mentioned wearables. I didn't really explain why soft and stretchable stuff is interesting, but just 30,000 foot view, the idea is if, electronics are sort of in every aspect of our life, and the ability to make them soft, the vision here is to be able to put them sort of everywhere, whether it be in clothing or in a seat of a car or implantable devices or something directly worn on the skin. And this is a little bit science fiction-y, but if you think about the human body, we have rigid components, which basically are the bones. But if you take that part away, then most of our tissue is soft, and it's able to do amazing things, including logic and memory and sensing and all these things. And it's done entirely with soft, stretchy materials. Of course, there's a limit on how stretchy your skin is, but
sure, anyone who's torn an Achilles tendon knows that. But
yeah, exactly.
But your point is right. We connect hard surfaces, bones, with tendons, which are stretchy and can shape shift to a degree. And I would imagine even gallium loses its infinite ability to stretch, because the more you stretch it, the narrower the diameter becomes. Again, stretching a piece of gum, as you talked about earlier, at some point you run out of gum, right? It's too thin, but I guess that can be built in. You did something that I find very enviable. You gave a TEDx talk a while back. That's one of my bucket list goals, to come up with something interesting enough to be able to give a TED talk. But you mentioned, you made a comment there that shape defines function. And you kind of touched on that a few moments ago. Expand on that if you would. Tell me how shape defines function.
Sure. So I'll sort of answer that in two ways. One very general, then I'll give a specific example. But from the kind of the most general perspective, the basis of manufacturing is you take raw materials, which are come typically as, just chunks of material or little pellets of material, whether it's plastic or pieces of metal or whatever. And the whole idea of manufacturing is to take those raw materials and convert it into some useful form. So as just a simple example, maybe you can imagine a milk carton or grocery bag or something like that. Well, the raw materials in that case is little plastic pellets, but it's been shaped into something that's useful. So that's probably stating the obvious. But in the case of electronics, this is really particularly true because the way that we shape and position, it's not just the shape, but it's also the location of different materials dictates the way that the circuits work. And in the case of liquid metal, I think there's one really nice example where an antenna is just a conductor, and it's a conductor that's designed in a certain shape to achieve a certain type of behavior. So, for example, there's Bluetooth and Wi-Fi and all these different types of communication devices. And as far as I understand, just kind of a layman's understanding is that the difference is just the way that they're designed and shaped. So one thing that we've done is basically take advantage of the fact we have a soft conductor it's got really good metallic conductivity, but we can also either move it around, and there's some tricks to do that, or we can put it in a piece of rubber and like literally mechanically change its shape by stretching it or squishing it or something like that. So we've made antennas that actually change their function. And what function in this case would mean resonant frequency, efficiency, stuff like that.
That's so funny you say that. When I was young, there was no cable TV when I was a kid, and my father had an antenna on the roof of the house connected to a motor that would rotate that antenna 360 degrees in so many degree increments, and he had this knob on the TV, which was the controller for the motor, and it had all these degree marks, probably 5 degree increments. And he got his Dymo labeler out. Remember those the little plastic strip of embossed letters and numbers? And he would rotate the antenna until channel 2 came in clearly. And then he would put channel 2 on the Dymo labeler and stick that on the markings, on the graduated markings on the controller. And then he'd rotate it again, turn it to channel 4, and then rotate it again until channel 4 came in clearly. And then he would label channel 4. And I think there was about 8 or 9 stations back in those days. So around the label, with all the little graduations, were little Dymo labeler markers with all the 7 or so television stations we had. That was his way of taking a rigid antenna that did not shapeshift, but still managing to change its orientation so that he could, maximize the reception on each of the local television stations, broadcast signals. That would be a lot easier if the thing would just change shape, on its own. That would have been easier. That's one example. Before we're just about to kind of dive into the science of it, which I'm excited to get into. But let's just kind of look at the potential 800-pound gorilla and kick him out of the room. There's a lot of examples in our world of wonderful technologies that's benefited humanity, but at a price. Maybe the price is toxicity or danger. I'm thinking of X-ray technology, for example. Wonderful technology. We do so much with X-ray, not just on the human body, but inspecting things that we could normally not inspect. In our world, in the electronic assembly world, we use X-ray a lot to look under bottom terminated components like BGAs and QFNs, because otherwise you can't see. And that's helped us improve reliability. I'm thinking of energy generation, the whole atomic power, nuclear power. Wonderful technology, but it has a dark side, potential dark side, if something's not done safely. Does gallium have I know mercury, I mentioned in our opening that, our science teacher used to pour mercury in our hands. which may explain some things about me. Who knows, in my generation. But does gallium carry any level of known, and I'll emphasize it with known because we don't know what we don't know, but based on what we do know, what's the safety element or the toxicity or lack thereof of gallium?
Yeah, so I can elaborate a little bit on this. So the first thing is you hit on something, which is I think there's things that we don't know, and so people that are listening to this should be cautious. But that said, everything that I've seen and learned about this material suggests that it's got low toxicity or it's just non-toxic. So one kind of just perspective thing is that if you think about why is there this perception that liquid metals are toxic? Well, it's basically just because mercury is toxic. And I would argue that there is no correlation between toxicity and melting point of a material, right? I mean, just think about water. Water melts at 0 degrees, gallium melts at 30. So the melting point really has nothing to do with toxicity. It's just that the only liquid metal that people tend to think of is mercury, and that is toxic. So the fact that it's a liquid metal is not necessarily what would make it toxic. But that said, it's still a material, and the truth is it's not a material that's found in our natural diets. It's not even a micronutrient. But several studies have shown that if you were to get it in your body treats it very similar to iron, because gallium and iron have the similar ionic radius and similar charge. So your body's able to flush it out. And it's actually been FDA approved for a number of different applications. So you kind of have to clarify a couple things. So there's gallium metal, and then there's gallium salts. And just like if you were to take a vitamin in the morning and like my wife used to take iron supplements. Well, you're not eating iron metal, you're eating an iron salt, because iron metal is not going to be soluble in your body. So so gallium salts have been FDA approved for a number of different applications, which means that people have put it in their body and shown that it gets flushed out. And the other really interesting thing about gallium is it has no vapor pressure. So unlike other liquids, that evaporate, this one does not. So it means you can handle it out in the open and don't have to worry about breathing it. So the only way that it could really get in your body is if you intentionally rubbed it on your skin or you put it in your mouth or something like that. So I would not do that. I would recommend not doing that.
Don't try this at home. Yeah.
Don't try that at home. But like I said, everything that I've personally seen suggests it's not a problem. And I mean, I know I've personally got it on my skin before, and it's you just wash it off with soap. You can actually buy gallium directly from, I don't know if I can say names, but there's very common, like Amazon. You can buy it on Amazon, and so it's not an exotic material in that sense. But again, I would be a little bit careful just because it hasn't been thoroughly studied. But every study that I've seen suggests it's got low toxicity. In fact, we had some work. It was a collaboration with a colleague, and it was really their idea, but we helped a little bit. But the idea was to use liquid metal particles, like really small ones, and use them for drug delivery. So we showed that we didn't do it in humans, but we did it for killing cancer cells and in mice. So we actually went so far as to put the actual metal, so not the metal salt, which is FDA approved, but the metal into to mice and showed the different clearance mechanisms by which the body removes it.
Wow, that's interesting. You mentioned, kind of as an aside, but it caught my attention. Did I hear that correctly, that the metal state for gallium begins at 30 degrees?
Yeah.
Which is about 86 degrees Fahrenheit. So it's right now in my room, in my house, it's probably 68 degrees in here or so, Fahrenheit. So would it be in a solid state then? If I bought it from Amazon and opened up the package, would it just be a solid metal at that point?
So it might be, but there's another two very interesting things about gallium. So one is that, yes, it melts at 30 degrees Celsius, so about 86 Fahrenheit. So that's, if you held it in your hand, that's enough to melt it. But like you said, inside in a temperature controlled environment, it would should be a solid according to thermodynamics. But the reality is that it will supercool. And this is something other liquids do, including water, but this one really supercools. So it melts at 30 degrees, but it freezes well below that. In our lab, we've seen it as low as, I think, negative 40 Celsius. So that means it's actually quite difficult to get it to freeze. And so there's that, but ultimately it will freeze. And then the other thing is you can mix other metals into it and lower the melting point.
Okay. Yeah, I think
just
we're going to get into that. I remember seeing that on some of
Yeah.
your earlier broadcasts. Is it eutectic? Does it have a plastic state, or does it go, 29.9 degrees? Well, it sounds like there's a different definition of liquid, because you're saying its freezing point is extremely low. What's the difference between its frozen state and its non-liquid but non-frozen state? So, 20 degrees C, for example. What will it be malleable at 20 degrees C? Will it appear to be liquid at 20 degrees C?
Yep, it'll still be a liquid.
So there's a difference between kind of semi-liquid, for lack of a technical term, and fully 30 degrees plus, 30 liquid.
So pure gallium is either going to be solid or liquid. You can't really have both unless you're right at the melting point. So,
Right.
It's, if you think about like ice water or something like that, you can have ice water where you have solid water and liquid water for a short period of time, but it's not at equilibrium. Eventually, either the ice melts or the water will freeze.
Right.
Now, if you could hold that water at exactly 0 degrees, you could have the two phases coexist. And gallium is exactly the same way. If you held it right at 30 degrees, you could have some solid and some liquid together. But otherwise, if you're above that temperature, it's 100% liquid. And then if you're in this, what I call the supercooling state, it's still 100% liquid. And then when it freezes, it just becomes completely solid.
Right. I'm going to switch over to have you share your screen, because one of the questions that came into my mind, and I already know the answer because I cheated and watched some of your prior interviews, but I'm sure that a lot of my guests right now are wondering, there are times when we want our conductors to be rigid, and then there are times when we need to change the shape of our product. We want it to be less rigid or liquid. And one of the first questions I had when I first heard your topic before digging into it was, well, which is it? Is it solid or is it liquid? And obviously what you have worked on for all these years is a way to get the best of both worlds, to take a rigid metal, instantly turn it liquid, and then when it's at its desired shape, then instantly convert it back to a solid again, which I find fascinating, because that is not the normal property of metal, is one or the other, unless you put it through some severe environmental changes. I think of castings, for example. You take a solid metal, you melt it down to a couple thousand degrees, you pour it in a mold or a casting, and then you let it cool, and now you have a new shape. Now, obviously, we can't do that in the circuit assembly world, because other components would not be happy with that. So I'm gonna switch to this view right here, and let's make this the Michael Dickey show. I'll let you drive and explain to our audience what we're seeing and how we can go from a solid state to a liquid state with the exact same material.
Yeah, so you've actually hit on two different ideas that or two different ways that you can achieve what you just said. So one is,
I'm sorry to interrupt, Michael. Let me just say before we get into this, for those of you listeners who are in the car wondering what the heck we're talking about, what we're seeing, there's not a really good way to provide kind of a closed captioning version of what I'm seeing here on the screen and what our audience will see on the screen that are watching this on YouTube. So let me just suggest that for this particular episode, the visual assets that Michael is going to show are so compelling and so interesting and exciting. go ahead and finish your drive or finish your workout on the treadmill while you're listening to this podcast. But consider when you get to a location where you can watch this, go to our YouTube channel, just search Reliability Matters, and find this episode. It's number 111, and you can see. So you don't have any FOMO. There's no fear of missing out here. You'll be able to see some of this extremely interesting video and other visual assets here. Sorry, Michael, I didn't mean to interrupt, but I just wanted to get that part out of the way in case half my audience is going, what are they looking at?
Yeah, thanks, Mike. The work is very visual and definitely worth checking out. So I hope that you will take the time to look at it. So Mike mentioned there's this idea of going from solid to liquid. And so I'd like to clarify, with this material, you can do sort of what's intuitive, which is to freeze the material and actually make it so that the whole thing is solid. But what I'm about to show you is actually a different idea, which is basically the metal is a liquid the entire time, but we're taking advantage of this oxide shell that naturally will form on the surface of the metal. So what we're looking at here is a printed structure, and there's a reflection. So it's sometimes people don't see it right away, but we've written out the word liquid using liquid metal. And there's a syringe that's dispensing little droplets of the metal. And the reason it's able to hold in this shape is because of this 3 nanometer oxide layer that naturally forms. It's just simply the metal reacting with oxygen in the air to form this shell. And I've got a video to show exactly how we did this. And so to really drive home the importance of this shell, I've got this video here in which we've got some of the metal spread on a glass slide. And it's in this, looks like a kind of a puddle, but if you use this Q-tip, which has acid on it, hydrochloric acid, that acid will dissolve away the oxide layer. And without that 3 nanometer thick oxide layer on the surface, the metal has an enormous surface tension and it just will beat up into a droplet. So this is kind of what you would expect if you were playing with Mercury. I think at the beginning of the show, Mike mentioned how Mercury would form like a perfect sphere and it can break into little droplets, but it's always spherical. That's because metals have enormous surface tension. Liquids have surface tension. Water is, from your day-to-day life, water is probably the liquid with the largest surface tension. And without getting into units, water surface tension is 72. Well, this metal depends on the environment, but it can be as large as 700. So what I like to tell people is that, if most of your life you walk around, most people are, somewhere between 5 and 6 feet tall. And that's like normal liquids, but the liquid metal would be like seeing a 50-foot tall person. It'd be very, very weird. It's so out of your normal everyday experience. It's hard to even imagine. And so anyway, that's why this is so interesting, is that when you think about metals, they should just form droplets, which is not that useful for electronics, but because of this oxide, you can pattern the metal. So to illustrate this is a video in which we've got a syringe and we dispense the liquid metal and it forms oxide so rapidly. And you can actually see the oxide if you suck the liquid back into the syringe. It kind of wrinkles, just like deflating a water balloon or something like that. But anyway, we dispense this little droplets from the syringe, and the oxide forms so fast and is sufficiently strong that we can start stacking those droplets. So if you imagine trying to stack droplets of water, you would just end up with a big puddle, or tea or Coke or any sort of other liquid. And the oxide forms so fast, in fact, that you can do a little burst of pressure and it will shoot the metal out of the syringe, and it oxidizes so fast that it will actually form a fiber, kind of like Spider-Man. And what we're looking at here is also kind of fun, but this is a dead bug that we found in our lab. And my student did this as a joke, but basically he's printing antenna on top of the dead bug. And he did it as a joke, but it really nicely shows how small these structures are. They're about the diameter of a human hair, on that length scale. And we're able to print at room temperature. So this is truly ambient patterning of metals. So this kind of cuts to the heart of it for electronics, is that, there's all these ways to pattern metals that are used in electronic chips and stuff like that. But the fact that we've got a liquid, not only does it allow stretchable and soft devices, but it also allows new modes of patterning. So there's the 3D printing. You can also inject it. So what I'm showing here is we call a microfluidic channel. It's just a piece of rubber that has a tube built into it, which we actually pattern by lithography. If you apply a little bit of pressure, you can basically squirt the metal from a syringe into that little tube, kind of like filling a straw with water or something like that. And the pressure from your thumb is enough to break that oxide layer, because remember, it's only 3 nanometers thick. It's like a thin layer of glass, very easy to break. And because of the low viscosity of the metal, it's like water. You very low viscosity, you can push it into the channel, but once it's in there, it reforms that oxide. So it's sort of like I don't know. It's sort of like a waterbed naturally forming its own shell, and that holds it in that shape. The end result at the end of the day, in this particular case, we've injected it into a slab of rubber. It's a silicone. It's a rubbery material, stretchy. So if you put this into a rubbery material, you can make a wire that is as conductive as a metal because of the liquid metal, but is stretchable as rubber. So in this case, we're looking at basically a rubber tube that's filled with the liquid metal. And I'll play it, and you're going to hear some sound that's coming out of these. We've basically converted these wires into headphones. And as we stretch it, there's going to be no degradation in sound quality. So here we go. So we're starting to play a little bit of music through these headphones, and it'll get louder here in a second. But so you hear there's no degradation in sound quality. And we're stretching these wires to hundreds of % strain. So I think that at max it goes to about 8 times its original length.
Wow.
So if you imagine you have a wire that is, I don't know, 1 or 2 feet long, and you could stretch it to the height of a basketball goal, like it's really, really stretchy. And of course, if you made this more like a telephone wire, you'd get even further. But this is just a straight wire that we're extending past its original length.
So I would assume that as it stretches the diameter, basically the equivalent of the gauge size of the wire, will be reduced. So its current capacity, electrical current capacity, would be reduced the more we stretch it out. So if that's the application, one would have to look at the maximum stretchable distance and make sure that it's still got the appropriate diameter to it to carry the desired current load. Is that correct?
Yeah, that's absolutely right. So that feature is either a bug or a feature, depending on how you look at it.
Sure.
So some people have used that to create strain gauges, soft stretchable strain gauges, or also sensors of touch, taking advantage of the deformation that can happen in the cross section of your wire and using that to sense, actually very sensitively, can sense touch. So that's the feature part of it. But the bug part of it is, you're absolutely right. When you stretch it, you change the geometry. You make the wire longer. You also make it narrower, and therefore you change its resistance. Now, the resistivity, the material property, does not change. You're simply changing the geometry,
right,
by stretching it. And the reality is that this is a really nice demonstration because it can stretch really far. But for most applications, like if you were going to say put this into clothing or something like that, the most strain that it would probably endure would be something like 30% strain.
right.
So just a small fraction. Like you imagine putting something around your elbow where you bend your elbow. Well, today I'm wearing a sweater because it's kind of cold here in North Carolina, but my sweater is just the knit pattern of my sweater is able to accommodate that strain pretty easily.
Sure.
So you wouldn't have huge changes unless you really had an application where you really had to deform it a lot.
Yeah, and many applications are not carrying current loads. They're sensing. They're signal carriers, not so much huge amperage carriers. I think we have conductors that work well for that. And I can't imagine a 200 amp gallium circuit that would be pretty gnarly. Does gallium conduct as well as other metals, copper and gold and things like that?
Yeah, that's a good question. So it's not as a good conductor as copper, which is one of the better conductors. And I don't remember the exact number. I should have it memorized by now, but it's something like and about an order of magnitude less conductive. I think maybe factor of 15, something like that. So it's still considered to have metallic conductivity, but not as good as copper. So, I've always kind of argued that you would only use this material if it gives you some advantage that you couldn't get with copper, because gallium is expensive. And, for the amount of material that we're using in this example of the stretchy wire, it's a few pennies worth of material.
Right.
But still, it's more expensive than copper. And then it's also not as good of a conductor. But on the flip side, if you were to compare it to, like, say, salt water or something like that, depends how much salt's in the water, but it's at least 1,000. I think it's maybe 10,000 or 100,000 times better conductor. So compared to other liquids, it's far superior, but compared to other metals, it's a little bit worse. I mentioned earlier that kind of the science fiction motivation here, there's the aspects of skin. So skin can conduct signals and it can sense and do all this stuff. Well, another thing that skin can do is heal. So just yesterday, I got a little cut on my finger and it sort of hurt, but today it's almost better. It's a miracle. And if we basically have taken advantage of the liquid metal properties to do this. So what we're looking at here is a liquid metal wire that's conducting electricity, and the electricity is lighting up an LED just so it's kind of visual. And we completely cut this device in half. We're literally taking a pair of scissors and cutting it in half. And of course, when you cut it in half, you break the circuit. So the light bulb turns off. It's no longer conductive. But when we bring the thing back together, that metal, when we cut it, it oxidizes so fast that it stays flush with the cut interface. So when you bring the two pieces together that you just cut, put them back together, because it's so soft and it's a liquid, basically that the oxide will break and the metal wire goes back together. So we're now seeing that the light bulb is turned back on because there's electricity going through the circuit again.
That is very T-1000 Terminator 2.
Yeah, a little T-1000.
Self-healing, yeah, for sure.
Yep, self-healing. But what makes this sort of special, so it heals electrically, but there's also a shell of polymer that we've built around this as kind of like the insulation in an electrical cable. And it's made from a special polymer that's held together by hydrogen bonds. So as you might remember from like freshman chemistry or something like that, hydrogen bonds are not as strong as covalent bonds, but there's enough of them here that it holds the material together. And they're reversible, so you can break a hydrogen bond and it can go back together. Whereas normally when you cut a material in half, I mean, I've got all sorts of stuff from my office, but if I were to cut pretty much anything in my office in half, I'm not going to be able to put it back together.
Right. And once it self-heals, is the connection integrity as if it never happened? Is it just back to one complete piece again rather than a patched, two patched pieces put together?
Yep. So, as you look at this here, you can see where the cut was made. So we didn't line up the two pieces perfectly. So there is a little bit of an edge there that you can see visually, but otherwise the polymer has gone completely back together, and the metal, to the ability of our lab to measure this, we don't see any changes in resistance before and after. So basically it goes back together. We've regain the mechanical properties. I believe it breaks at slightly lower strain than a pristine material, and that's probably because there's a little bit of a crack there where stress can concentrate. But otherwise it's regained its original modulus. It's stretchable, and like I said, the electrical conductivity is, to a first approximation, almost identical to what we started with.
And because basically it's a liquid. Its natural state at that temperature is liquid, and you're applying current and other ingredients to cause it to solidify. It will never suffer from metal fatigue like traditional conductors would.
Yeah, that's right. Yeah, so we haven't published this, but we've put some of these wires, now not this particular one, but like the headphone wires, we've put them into a cyclic strain apparatus, basically something that can stretch it over and over again. And it's squeaky and really drives people crazy in the lab. So we don't do it all the time, but when we've done it, it's typically fails or actually never fails. We get up to like 10,000 or 100,000 cycles, and typically what happens is the polymer breaks before the metal.
Sure.
So the metal's not a problem. Now there is this interesting question that you remember we've talked about the importance of the oxide. So if you have I don't know, a wire or a piece of rubber or something that you stretch, well, every time you stretch it, you could potentially be breaking that oxide, and then more metal would oxidize. So in principle, if you did this enough times, eventually you would consume all your metal. But we haven't seen that, and I don't have a good explanation for it. It could just be that it provides a good barrier to additional oxidation, or it could just be that we haven't stretched it enough times. But the point is
when I think of when I think of metal oxidation, back in my soldering days, with the wave solder machines, you would always have this thick layer of dross on top of the solder pot, and that dross could be reclaimed, but it could never be successfully mixed back in to make it a homogeneous material. It was a loss, and if you just ran a wave solder machine, ran the pump, and never actually soldered anything, you would still consume solder because you have to keep removing the oxide layer as it gets chunky and thick. So to your point, this doesn't seem to have at least a measurable loss. The oxide layer, once the right application of either current or whatever is applied, the oxide layer seems to just kind of blend right back into the material and not constantly float on top. Is that right, or is it always there, just in a different shape?
Well, sort of the spirit of what you're saying, I think, is right, but it doesn't mix back in. Well,
okay.
It can mix back in. If you stir this material, you can actually get flakes of oxide to go into the metal, and that's something that we and other people have shown recently.
But that would be a contaminant then. It's not really.
Well, that's how I looked at it. That's how I looked at it initially. But actually, I think in general that's true. But we were doing it on purpose because we were trying to change the rheology of the way that the metal flows. We're trying to change it from being water-like, like the bulk property to be like water, to something that was more like toothpaste. And that's interesting because of the way it dispenses when it comes out of a needle. I don't know if you remember the video, but when we're dispensing it out of a nozzle, it comes out as a droplet.
Yeah.
But if you can change the way it flows, then you could actually extrude it as a more like toothpaste, like a cylinder.
Sure.
So we've been doing it for that purpose. But in the case of the stretchy wire, my feeling, and I don't have proof handy to prove this to you, but my feeling is that oxide layer is just on the surface.
Okay.
It's breaking, probably reforming. And if you look at it over time, I mean, I've got a little sample here that I've handled a whole bunch, and it's going to be a little bit hard to see, but it's the NC State logo. Over time it starts to look.
Go ahead and hold that up again, Michael.
Yeah. So this is the liquid metal pattern in the NC State logo, embedded in an elastomer. So I can pull on it. You can see it's.
Oh, look at that! Wow.
Moves right along with the elastomer. And
it reminds me of silly putty when I was a kid. We would put silly putty over a comic strip and pick up the ink and then stretch it out to make it look funny.
Yeah, a little bit. I mean, this is elastic, so it's it's not going to flow like silly putty, but yeah, sort of similar. Anyway, it's a little bit hard to see on the camera, but this sample, the surface looks a little bit dark, just because I've handled it a bunch. Probably got some oil from my hands and that oxide breaking and reforming. But again, if we were to do careful electrical measurements, we've done this and other people have done it. You don't see a change of resistance over time. Now, if you made the wires really small, probably that 3 nanometers of oxide could be significant. But for most applications that we're working with, we're dealing with wires that are more like, like a human hair, more like 100 microns or so.
Was there more? Do you have more graphics for us?
Well, I do have one other thing that's
cool.
Maybe a little outside the realm of your audience interest, but from a science perspective, very cool. So we're looking at a vial of liquid metal, and it is sitting in a base, sodium hydroxide. So it's just a clear liquid that's got a really high pH. And that high pH is important because it keeps the metal free of oxide. And when you shake this thing, this little vial, the metal will break up into droplets, kind of like when you shake salad dressing.
Yes.
But unlike salad dressing, remember the surface tension of this is really large. It's like the 50-foot tall person. And so it very quickly phase separates. It goes back into one droplet.
Yeah, for the sake of our listeners only, you have one droplet of liquid metal. You're shaking it up. It breaks into 30, 40, 50, 60 smaller droplets. And then within just a few moments, when you stop agitating it, it's all coming back together into one single droplet again. It's just popping back into shape.
Right. And there's no oxide here. So this is driven entirely by surface tension. So we don't have that solid coating. So this, for one, it illustrates why the oxide is so important. The metal naturally wants to form a droplet, but it's only because of this oxide that we're able to shape it. But it also illustrates that the surface tension is really large. And one thing that we discovered a few years ago was, and this was on accident, which was really interesting, but that if you put it in this solution and you apply a voltage to it, and this is only in the solution, this is what's called an electrochemical reaction. Basically, you're going from, the metal conducts electrons, and then when it comes in contact with the water, you have to have some reaction occur because the water conducts ions.
Right.
Well, that reaction is the oxidation of gallium. And from everything I've shown you, what you would expect is it would form a solid shell. It's like the waterbed where you can make the shell appear and disappear. But what's interesting, and we're still trying to understand this, is that when we do it under these conditions, it actually lowers the surface tension significantly. So it's like taking that 50-foot tall person and making them basically disappear. So I'll show you here. We've got a video where you're looking top down. So gravity is kind of into the screen. And we've got, 5 droplets of the metal. And it's sitting in that solution. So it's really high surface tension. And when we apply a voltage, so there's an electrode underneath each of these drops, the metal will spread and adopt the shape of the little cavity that it's sitting in. It's like kind of like a little ice cube tray. And so we've got a triangle and a star and whatever. And so basically we're lowering the surface tension. Gravity squishes the liquid into that little container. And then when we switch the voltage off, whatever was on the surface dissolves away and it beads back up. So
that's as close to a really casting. Cool. That's as close to a casting example that I could see. Instead of pouring it in, you just place it in its normal round spherical shape, and then when you apply current to it, gravity just stretches it out into its mold, so to speak.
Yep.
Oh, that's amazing.
And I don't want to confuse anyone. Again, this is a unique set of circumstances. So if you did this in air, it would not work. This has to be done in this electrolyte. But it's really interesting because earlier we talked about shape defining function. Well, here we're not making shapes that have really any utility, but it illustrates the idea that you go from a spherical shape into like a star or something like that. So you can imagine if you maybe had like an antenna or something like that, where you can change the shape and tune the frequency or even move the antenna from different places, kind of like what your dad was doing up on the roof with the rotating antenna. So just, I guess, one more gee whiz sort of thing, but this, what we think is that the surface tension under the right conditions is basically going to zero. So, Mike, you know that I'm a teacher. I'm gonna quiz you here. Uh-oh. What happens to a liquid when there's no surface tension? What will it do?
It flattens out.
Yeah, there should be no energetic penalty for gravity squishing it down. It should just spread and spread and spread. So, what I'm showing you here is a syringe needle, basically, that's about the size of a human hair. So it's very, very small, about 100 microns. And we're going to pump the metal out of the nozzle. And initially you're going to see it's going to form droplets. And that's exactly what you would find like on a drippy faucet at home. If you just kind of turn on your faucet very slowly, it will form droplets. And same thing if you even have like a garden hose, it forms a cylinder of liquid, but it will very quickly break up into droplets. And this has been known since the late 1800s. It's called Aurelian Stability, named after Lord Rayleigh. So this is just what fluids do to minimize their surface area. But as you just correctly answered, if there's no surface tension, there's no driving force for a liquid to beat up. So here we pump it, and you'll coming out of this nozzle, and you see it form droplets. Now we start applying a voltage to it under these special conditions, and the droplets get smaller and smaller. And then under the right conditions, it will come out as a straight wire.
Looks like a lightsaber there from
Yeah.
Star Wars.
And then if you apply too much voltage, you form a kind of a crusty surface, and it looks kind of like candle wax and starts really changing the way it flows. But the point is, it's really hard to appreciate this. But this is like it should almost blow your mind, because again, this is the 50-foot tall person. It's a really large surface tension, and so it really should form droplets. But because we're able to modulate the surface tension, which is a very strong force when you make things smaller and smaller, we can start controlling the shape in interesting ways.
And was that example pure gallium, or was it gallium mixed with anything else?
So that one was gallium and indium. And
indium, okay. Another low temperature solder.
Yeah, that's one of our favorites to use, just because it's commercially available, and its melting point's about 15 Celsius, so it's truly a liquid at room temperature. We don't ever have to argue with people whether it's a solid or liquid. Of course, in this case, it's obvious it's a liquid, but anyway, yeah. So I only had one other video, and it's just for fun. But
sure, let's see it.
Do you know who this guy is?
It's hard. I can't really tell on my teleprompter. It's a little too far away.
Oh, okay. So that's Seth Meyers. And
there you go. Okay.
Yeah, I think he lives in your neck of the woods, if I'm not mistaken.
I love his show, by the way. I watch his Closer Look segments all the time whenever I can.
Yeah, so for your listeners, he's started his, well, I don't know if where he started his career, but he's really became a household name on Saturday Night Live.
Yes.
And then he eventually started his own late night show, and he's really funny. Anyway, this was sort of a career high for me. He made fun of our research, so I'll play this. And
I got to see this. Yes.
Well, this week, scientists at North Carolina State University announced they discovered a way to move and manipulate liquid metal with electricity. And Arnold Schwarzenegger has already been sent back in time to stop it.
So that's kind of a career high for me, getting made fun of on late night TV.
That's amazing. That's awesome. That's awesome.
Yeah. So anyway, I've got lots of other fun videos I can show you, but I think the ones I showed you kind of capture the essence of this material.
Yeah. Oh, that's great. So before we wrap up, I just have a couple more questions, Michael. Outside, well, no, let's do this one first. No, let's go here. Outside of the electronics industry, what other industries or applications would benefit from the use of gallium in this case?
Yeah, so, well, maybe I'll mention first, within the electronics industry, there's some applications that aren't actually using the electronic features. So it's because it is a metal, it's a very good thermal conductor. And believe it or not, the most recent Sony PlayStation has this material in it for dissipating heat from the computer chips. As you and your listeners know, as transistors get smaller and they become more densely packed onto a chip, there's a lot of heat that's got to be dissipated, and metal is about the best thermal conductor you can get. And if you just put a slab of metal like copper on a computer chip, there's always going to be a little bit of an air gap between the chip and the piece of slab of copper. So,
and thermal dissipating paste
and then
dries out over the years, right? It's not really a permanent solution. So gallium, a liquid metal, then would automatically form the shape it needs to form. It will fill every gap, which makes it a better surface conductor, right? You don't have those little voids you would with a rigid surface. As much as you can pre-shape the rigid surface, it's still going to be small air gap in there, which will generate heat.
That's right. Yep. So it's being used literally. The most recent Sony PlayStation's using it. So some of you might already have it in your living room and you didn't even realize it. And up until recently, I think you could go to like Walgreens and buy a thermometer, old-fashioned thermometer that had gallium in it. But these days, the digital ones are so cheap and so good, I'm not sure that they're even still in the market. I've happened to have one that I just have sitting here in my office that I bought at drugstore. I don't remember if it was Walgreens, but So anyway, there's those kinds of things, and also still within the world of electronics. A lot of your listeners probably know of semiconductors like gallium arsenide, gallium nitride, that are also commercial. And so in that case, the gallium is not a liquid; it's just a precursor that gets reacted to form those species, and those are very interesting semiconductors. So, kind of, I think within the world of electronics, that's probably about it. Although there are interesting tools ones that's called focused ion beam. Is that something you've heard of before?
I have,
Mike?
in the test world.
Yeah. Mm-hmm. So yeah, people use them, as far as I understand, to fix metal conductors that have like little defects. You can go back in and deposit material. Well, the source, the ion source in a focused ion beam is typically gallium. So that's another place where some of your listeners may have encountered it and either the forgotten or just not realize that was inside the tool. But for outside the world of electronics, as far as I know, there's no commercial applications. But I do know that there's at least 3 companies that I know of. One of which is a pretty big company that probably doesn't want to be named, but that are working with these materials to try to make electronic devices, to make them all the things we've talked about: soft, stretchable, comfortable, to be worn against the skin. But
I think as IoT just it continues its explosion, there will be uses for stretchy, malleable electronics. Clearly,
I think so too.
Wearables has proven that. Medical, I'm sure, when there are what look like mesh patches that one can put on their skin that are actually small circuit assemblies, sensors of certain things, certain sorts. The automotive world, for heat dissipation, that's a huge thing right now, particularly with the electrification of cars. EVs are constantly battling that. It seems like a product in search of an application, and
that's how I've described it to people. It's like a solution looking for a problem. And there's so many unique properties about this material that there are things that it can do that are truly unique that, as far as I know, nothing else can quite replicate. And so
it's kind of interesting to me that. Sorry, I didn't mean to cut you off.
No, go ahead, please.
It's interesting to me that gallium is a interesting product that doesn't have a lot of commercial application, yet you can buy it on Amazon. And it just makes me wonder: is it a party trick? For the people who buy it on Amazon outside of your world, you're buying some, your students buying some, researchers, things like that. It does seem for the layman, for the civilians in the world, it seems like a little bit of a party trick because it's a safe version of Mercury, for whatever. But it does definitely have some applications, and the work you're doing is fascinating. Where do you see the future of your work and your research and the application within our space? Where do you see that going?
So you mentioned the party trick thing. I just want to comment on that. So there's a fantastic book, if you're into science, which presumably your audience is, on the history of the periodic table, which I realize sounds kind of like a snoozer, but there's an author, Sam Keen, who really made the history of it come alive in the pages of his book, which was called The Disappearing Spoon. And the title is actually a reference to gallium. So there's this parlor trick or party trick where you mold gallium, you melt it and you mold it into the shape of a spoon. And then you give it to somebody to stir their coffee or to stir their tea. And when they pull it out, there's nothing left of it. It just, has disappeared. And of course, it's in the bottom of the coffee, but you can't see it because it's just melted.
Right.
So the book is called Disappearing Spoon in reference to that. But yeah, so I wanted to touch on something you said earlier, which sort of maybe transition into your question, but it's, the applications outside of electronics. There's a growing number of applications. And again, there's nothing commercial that I know of. But one of the things, at least for me and sort of my small community, is people are calling soft robots. So, when most people envision robots, they're imagining, at least for me, I imagine like the plant floor at like Ford Motors or something, where you've got these rigid robots and sparks shooting everywhere. And it's just not a safe environment for humans. So if you contrast that to the human body, or even something like a jellyfish or an octopus that can do these amazing things using soft materials. So there's this interest in using liquid metals and other stuff too, but to build robots that contain some of these materials, so they could safely well, first of all, safely interact with humans, number one, but also be able to do things that just simply can't be done with conventional robots. So if you think about like a mouse or something, it can scurry across the floor, contort itself to go under a door or a small gap, and then continue on the other side. So this was something I also learned about during my postdoc, and there's a big field of people that are working in this space. So there's that, but also one thing we didn't touch on that's, again, maybe tangential to interest of this audience, but gallium has also got some interesting properties for reactions, chemical reactions. And to give you a real poignant one, people have shown you can use it to reduce carbon dioxide. And so this is a very, very timely topic.
Yeah.
And with catalysts, catalysts are just materials that help lower the barrier for reactions to occur. And they're used for all sorts of things in our day-to-day lives. But when you have typically catalysts are solid, and when you form, let's say, if you could convert CO2 into carbon, it's like converting it back into charcoal, right? This is a good thing. But that material would typically stick on the surface of the carbon, and it's a special word for it called coking. Well, if your catalyst is a liquid, the material doesn't stick very well, and it will just flake off. So we have some friends in Australia that are leading this work, and they've shown that you can use these materials to do some of those reactions. So, I mean, I've got a long list of other stuff. I mean, it's got antibacterial properties. You can use it for 3D printing, but I don't want your audience to think that gallium is the solution to every problem in the world. But it really does have some unique properties, and depending on how much interest there is, I could elaborate. But
sounds like gallium. To sum that up, gallium is kind of an undiscovered country. It's a element that has a lot of potential once we discover all that potential. And history has proven that there have been these elements and other things around that have been with Earth for forever, and just now or in their moment, have been discovered that they have these miraculous abilities to either cure or create or react with something to make something better or to make something new. So gallium seems to be one of those that are kind of getting the spotlight. Are there other researchers besides yourself? I'm sure there are, but do you work with other researchers? Do you collaborate with other researchers that, for those of you who are into gallium and are kind of discovering new and potential applications for gallium? Is there a gallium club out there in the educational world?
They're starting to be. So, when I started my career a few years ago, there weren't a lot of people working on it. And there's kind of an interesting history. About 70 years ago, I think, or something like that, there was a paper that basically said, there's this gallium material. It would be really interesting, but oh darn, unlike Mercury, it reacts with air and forms this oxide. So people have known about this for a long time, but for many years, the oxide was considered like a bugaboo. It was like something you didn't really want.
That was a fly in the ointment, so to speak.
Yeah, exactly. Well, if you want a metal, you want a metal, but most metals oxidize, including copper and aluminum and stuff like that. So if I could take any credit, I think one thing that we've done is try to flip that on its head a little bit and say, for certain applications, that's certainly true, but for others, like for patterning the metal and making these stretchy devices and stuff. So
it becomes an attribute. It's not
like it's a feature attribute. Yeah. And so for me, it's not that we did anything brilliant, but we were just kind of at the right place at the right time. And in the meantime, other people have discovered some of this research, and we're not the only ones. There's a lot of groups actually in the U.S. now that are working. There's an explosion of research in China on this topic. There's researchers really everywhere. I mean, I could name names, but it wouldn't mean much to your audience. But I'm just happy to be here, to be the one representing this work. And I don't want to take too much credit, because there are a lot of, first of all, there's students in my group that contributed a lot. Everything I showed was done by students. They really deserve the credit. But the major advances that are coming out now are not always from our lab. They're from all over the place. And it's, I wish it was always from our lab, but it's also great to see that there's a community now of people that are working in this space.
Well, and also I think the work you're doing, since you've been doing it for so long, one of the earlier researchers on this subject, probably is, the genesis for other researchers to start, like he's onto something, let's continue it. So I think there's credit, not that you're seeking it, but I do think there's credit even from other labs that are discovering new things, because they may not have even bothered with it were it not for, former research that has gone on and inspired somebody. Michael, I really appreciate the work you're doing.
Thank you.
I look forward to seeing the applications. I look forward to the bragging rights when I can go. I knew him. I interviewed him on my show. I interviewed him just after Seth Meyers did. So I'll definitely take those bragging rights to the bar with me and use them. See what that'll get me. I will also post for our listeners and our viewers. Michael did a TEDx talk on this subject, and a lot of the videos that were on this episode were also on the TED Talk. But if you're familiar with TED Talks, they're wonderful because they explain things in a very understandable way, as Michael did today. But it's a good, fairly short, I think 18 or 19 minutes, 20 minutes or so. Easier to digest than this long format show. So I'll put that link on our site as well, and any other links that I find that are relevant.
When
Michael,
I prepared for that, I was joking that that might be the only thing my grandchildren know about me. So I really went to great efforts to make sure it was pretty polished. But my daughters like to torment me by turning that TEDx talk on and turning up the volume on our home computer and then playing it at half speed. So
you sound drunk. Yeah, I don't know. I'm an audio guy. Yeah, take any. All the podcast apps allow you to change the speed. So you can listen to it at 2x speed. I frequently do that if I'm trying to, down a podcast before I arrive at my destination, or 1.5 speed. But the funniest is to listen to any normal conversation at half speed. It just sounds like they are staggering out of a bar, trying to put a sentence together. It's so funny, and no one escapes that. No matter how good a speaker you are, played back at half speed, it's the funniest thing to listen to. It's the funniest thing to listen to.
See, I've not even watched it because I don't want to hear my own voice. And, so they already know that, and then they play it at half speed, and then they unplug the keyboard and stuff, so I can't stop it. And
they're great.
It's very cat and mouse. Yeah, they're figuring out like how to stymie me from turning it off. So
that's amazing. Get back at Dad.
Cool.
Yeah, that's great. That's great. And because you're not their professor, it's not like you can fail them, right? You can't threaten them with much. That will affect their whole life. So, that's great. Well, thank you for the work you do. Thanks especially for taking a little over an hour out of your life to be on this show. And thank you for educating me and my audience. It's a real honor for me to talk to you, and I appreciate the education you're giving me. You're a great professor, and you allow people like me that are not into the metrology of metals to understand. At least I can pretend to understand. I have a basic understanding of something I didn't know before. So thank you for educating me. I appreciate it.
It's been real fun. Thank you.
Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, or on our newest channel, Amazon Music, or virtually wherever you get your podcasts. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. Thanks for your questions and episode suggestions. Please keep them coming. Send comments or episode suggestions to Mike at mikeconrad.com. That's Conrad with a K. And be sure to subscribe to the podcast on your favorite podcast app. Or if you're watching this on YouTube, click the subscribe button and the bell icon to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of each month. Once again, thanks for listening or watching. Stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.